Well, should we start? Well, anyone from Nagpur who visited the science exhibition at VNIT? Those who are from Nagpur? Nobody? Daitwa, could you make it to visit science exhibition? Atharv, okay, you have been to. Have you seen those corn crushing and corn shelling machine, Atharv?
No, ma'am.
No? Why I'm
Yeah,
insisting is because the flywheel is used there. All those the three machines are kept in VNIT KVIC stall, and the first one is corn shelling machine, which removes the corn shells और जो corn के दाने होते हैं, भुट्टे के दाने, for removal of that, pedal operated. Next one is corn crushing machine. So the whatever stock is remaining, that needs to be crushed to convert it into powder. So that is for waste management. That is a corn crushing machine. And then third one is a briquette machine. So which will convert any kind of organic waste or bio waste mixed with cow dung in briquettes, which can be used in conventional chula, which is also used in what do you call it? As a fuel in general, as a fuel, wherever it is required. So flywheel is mounted there, and I'm teaching flywheel here, and I'm there in the stall almost every day. And I continuously I'm recalling all my students, they must come and see how this flywheel is working. So all that you have to do is just place a flywheel with the design that we are doing for its diameter, for its rim cross section, and how it absorbs energy, it releases energy as and when required. More so for a pedal operated machine where you have to pedal it and then you can relax and again pedal it and relax. So you get to know how when you are not pedaling and the work is still done, that is because this energy is stored over there. So Monday is the last day. I still insist those who can make it, they must visit the stall, at least VNIT KVIC stall, wherein we have these machines. And when you are here in the campus, maybe next month, we have a few bamboo processing machine, and in those machines we have flat belt, V-belt, chain drive, sprockets, gears. So everything that we are discussing here, it's there in those machines and it is fully exposed in those machines. And so you can definitely see those machines from the power rating. We can do the calculation and we can check the gears or the belt drives or the V drives and the pulley design that we are doing and that is placed over there. It is easy to correlate with what we are studying when we are seeing those things, which you can do otherwise also. Well, we'll solve two problems based on design of flywheel for IC engine as a prime mover. So this we discussed last class. Normally for IC engine as prime mover, in the question itself, some data would be given in terms of this torque, turning moment diagram, also known as T theta diagram, where along the vertical axis, torque is marked, and along the horizontal axis, theta is represented, where theta is the crank angle. This can be for a two-stroke engine, for a four-stroke engine. And area under this T theta curve, this is giving us the work done in one cycle of 4 pi or 2 pi, depending upon whether it's a two-stroke engine or a four-stroke engine. And this total work done upon the crank angle, this will give us the mean torque. And the area of the curve above the mean torque, this will represent the amount of energy which is excess energy, stored energy. So the power would be T mean into 2 pi in terms of N, depending upon what is N in RPM. So let us solve problems based on this. Whatever is the area above this T mean line, this is the excess energy. So from whatever data is given, all you have to do is find the value of del E. Once you get what is the excess energy released or stored, you know the remaining formulas for getting the moment of inertia, then mass, then diameter and cross section. Then we have to check it. Okay, let's start with the first problem. We'll be referring Shivalkar design data book. A 4-stroke engine. Take the problem statement, please. A 4-stroke engine running at 300 RPM, produces 18.4 kilowatt of power. Produces 18.4 kilowatt of power. If the work done during the expansion stroke, is 3 times the work done during the compression stroke. 3 times of work done during the compression stroke. Design the flywheel rim. Design the flywheel rim. Assume the work done during suction stroke.
Excuse me, ma'am.
Yes.
Ma'am, can you start the recording?
Yes.
Thank you, ma'am.
Reminding. Work done during suction and exhaust stroke. Is negligible. Does this recording thing really works? I doubt how many students they really listen to the recording for 1 full hour, but it's okay. Assume coefficient of fluctuation of speed as 2%. Assume coefficient of fluctuation of speed as 2% and T theta diagram as triangular. The turning moment diagram is assumed as triangular in nature. So for this IC engine, for whatever application, we have to design a flywheel. Torque is represented on y-axis, crank angle along x-axis, 4-stroke engine, so this is pi, 2 pi, 3 pi and 4 pi. A very small value of suction, compression, 3 times of this work done in compression is power stroke, exhaust. This is pi. Each of them is pi. Suction stroke, compression stroke, power stroke, and exhaust stroke. So your T mean is somewhere here. And this is the maximum torque. So this one would be the excess energy. We have to find out what is T mean and what is T max from the data that is given. So the power that is produced, this is T into omega, where this torque is always the mean torque into omega. This is rotating at 300 rpm, so 2 pi into 300 by 60, and power is known. Give me the value of T mean. Yeah, please remind me after the class. I'll share all the notes. But only if you have taken the notes on your own and if you have really attended all the lectures, that would be useful. Just based on my PDFs that I would be circulating, that would not be enough for your mid-sem. Give me the value of mean torque. $61.3. Any other answer? 585. 585 is correct. Mean torque is 585 Newton. 585.89 whatever Newton meter. This is correct. Now from the mean torque, how do we get the work done? Work done in the total cycle. Work done in the complete cycle or work done in one cycle. This is equal to area under this curve, which by formula is T mean into the crank angle for one cycle. This is work done. One cycle of a 4-stroke engine is the crank angle is 4 pi. And so here the work done would be this value of T mean, 585 or 586 into 4 pi. This is the work done. How much is this? $7,360. Correct. Newton meter. Now you know from the basic concepts of thermodynamics that this is positive work done and this is negative work done. This is work done on the engine and this is work done by the engine. Right? So these three are negative and this is positive, which is also shown here in the graph. For suction stroke and for exhaust stroke, this is negligible. So this is very, very small. So we'll assume this work done is 0 and this work done is 0. This is positive and this is negative, which means this work done per cycle, this is actually equal to the work done during the expansion stroke E minus the work done during the compression stroke. Right? This is positive and this is negative. So this minus this is giving the work done per cycle, which is 7360. And the problem statement also says that work done during the expansion stroke is 3 times the work done during the compression stroke. So can I write this as this is 3 times of work done during the compression stroke minus work done in the compression stroke is same as the work done in one cycle. So give me what is work done in the compression stroke and what is the work done in the expansion stroke. In compression it is 3680. Very fast today, great. During expansion is 11040, perfect. Wow, impressive performance. How come everybody is so much charged today? This is the total work done during the expansion stroke, right? This triangle. And this area of triangle is indicating what is the work done in the expansion stroke. What I'm trying to figure out is T mean is known. I want to find out T max. So that this area between T max and T mean, this is my difference of the energy or the energy stored. So for getting this area, I'm trying to figure out what is T max. And so this work done during the expansion stroke is area of this triangle. I need to name this triangle. Let me use small a, b, c. Let these 2 points be D and E. For this power stroke, this triangle is ABC and this smaller triangle is DBE. So the area of the triangle ABC, which is what? Half into base is pi and its height is T max. This is the work done in the expansion stroke 11040. Give me what is T max? You are right, Bharti, it is 7028, 7029. Or do I take it 7031, 7028? Newton meter. This is the maximum torque. Now, how do I get the energy stored, or how do I get the area of the shaded region? Area of the shaded region would be half of T max minus T mean multiplied by what is the base of the little triangle, is that DE, multiplied by the length DE. I'm drawing the same triangle here again. This is A, B, C, this is D, E. And we are interested in this area, where this is pi, this height is T max, this height is T mean. We want this area. How do you get DE? From the concept of similar triangle. DE by pi is equal to what? Sushmita? What is this length upon this length? Is that T max by T mean? No. Is that T max by T mean? Yes, it is T maximum minus T mean upon T maximum. So D is for this triangle. So base of this triangle upon base of this triangle. This is equal to height of this triangle upon height of this bigger triangle. So height of this triangle is T maximum minus T mean, and this height is T maximum. So everything known gave me the value for DE. This is coming out in radians. This. Perfect. This is 2.88. This is the crank angle, so this is in radians. And now once you know the value of D, you also know what is the amount of energy stored. Is that 9278, 9276, 9278? Correct. Yeah, you can go with your values. So this much variation is acceptable because some of you might have taken 2.8, others might have taken 2.87, 2.86. So this variation is very much acceptable. What next? Prajwal? What is the next step after getting this the energy stored? Yeah, so design of flywheel. So what? That is the design of flywheel is the topic that we are studying. What is the next step after this? Rotational energy, finding the value of I. What is the formula? This is equal to what? Arshita, I omega square into Ks. Ks is known, omega is known, del E is known. Give me the value of moment of inertia for the flywheel. Ujjwal, Anshuman, give me the answers, please. Are you there, Ujjwal? Anshuman? Yeah, give me the answer for value of I, moment of inertia. Is it 470? Anshuman, what is your value for I? 470. Units? Shreya, what are the units? Kg meter square. This is mass moment of inertia. Now the remaining part is what we have already done. In the earlier problem also, this is equal to mr square. You will have to Find the value of diameter, and for diameter you have to assume the peripheral velocity depending upon what is the power, less than 75 kilowatt, more than 75 kilowatt, from which you get what is the mean diameter. You get the outer diameter because this is a surface peak, and then you assume the mean diameter little less than outer diameter, which we'll check later. From this you find out what is the mean radius, assuming the material as cast iron. We know the density, this into velocity, where velocity is again pi rm or dm. If I take it dm, b into h, this is its volume. So this part, can you do it on your own? Should we go for the next problem? Utkarsh, Aditya. Is it okay if I leave this problem here? Because this part we have already discussed in the earlier problem that we have discussed. The rest of the problem remains same. We have to assume the peripheral velocity, get the diameter, get the radius from this formula of mass, density, assuming cast iron. You will get B into H. B by H is known. So you get the value of B and H. And then you have to check for what is the diameter coming out, outer diameter from mean diameter. And once this is known, you have to find out what are the stresses. The stress because of centrifugal force, stress because of bending. You have to find out the resultant stress, and if these two values are well within the safe region which is given in the design data book, then your design is correct. If it is not, then you'll have to change the diameter, change the value of B and H so that they still rise in this range. Okay, so since Utkarsh has said yes, nobody is saying no, or nobody is asking me to continue with this, let's move on to the next problem. Each problem here is different. I normally don't recommend machine design by Bhandari, but for this topic, I would recommend machine design by Bhandari because you have a lot of solved problems given there. So only for flywheel, you will get solved numericals and unsolved numericals, and you can refer that. But for rest of the topics and for the theory, I do not recommend Bhandari. Okay, next problem. Again, based on the IC engine as a prime mover. Design a flywheel. Design a flywheel mounted on a 4-stroke IC engine which is producing 75 kilowatt for remaining topics, I am referring machine design by Shingle. I am referring few more books on machine design for different topics. So it's not a single book that I have referred, but it's only for the concepts. For numericals, I have told you earlier on also, I am referring numericals on machine design by B.D. Shivalkar. So the same author whose design data book we are following, he is also having a book which has only solved numericals, solved and unsolved numericals. For solved problems, for unsolved problems, you can refer this book by B.D. Shivalkar, and for the concepts, you can refer Machine Design by Shigley, which is a standard book. So just to share with you, normally in final year, for those who are doing pure mechanical engineering kind of project and they come up with some design, and if in the panel where the final year students are presenting their topic, if Padole sir is sitting there, the first question he would ask is which book you have referred for machine design. And invariably students would answer, we have referred Bhandari, and the sir would get irritated beyond limits. And then he would say, normally, at least don't say that you are referred Bhandari, even if you are referring. First thing is you should not refer, and if you are referring, don't tell that you are referring this book. There are so many good and standard books that you should refer. So always refer Machine Design by Shigley. Well, design a flywheel which is mounted on a 4-stroke IC engine producing 75 kilowatt of power at 360 RPM. If the fluctuation of energy is 0.9 times the energy produced per cycle, and coefficient of fluctuation of speed is 1%. Find the mean diameter of the flywheel and cross section of the ring. What is the meaning of this statement? Fluctuation of energy is 0.9 times energy per unit cycle. What is the meaning of this statement? If someone can tell me the meaning of this statement, or how do we convert this in a formula? Visual. Fluctuation in graphs. Which graph, Prajwal? T theta diagram. So what is that indicating? What is that fluctuation indicating? Energy lost in the compression stroke. So you think 0.9 times the energy is lost in the compression stroke? Yes, this is delta E. This is the excess amount of energy which is either stored or released. That fluctuation of energy is that shaded part of the graph which we were discussing in the previous problem. So this is delta E, which is given as 0.9 times the total energy per cycle, or the total work done per cycle. So unless you understand this, you don't know how to start solving the problem. So this delta E is 0.9 times the total energy or the total work done. And for getting total work done, we must know what is the mean torque. And you know that for getting the mean torque, power is known, RPM is known. Get the value of T mean, power upon omega. This is rotating at 360 RPM. Give me the value of T mean and work done per cycle. which is the total energy per cycle, will be this T mean into what? Work done per cycle is what? This is the area under the curve, which is T mean multiplied by what? Beneath crank angle. For a 4-stroke engine, the crank angle is 4 pi. Yeah, now give me the value of T mean first. One nine nine zero. You are right. Newton meter. So what is the energy per cycle? It's 25,000 Newton meter. Or 25 kilonewton meter. Now the rest of the problem is simple. Del E is 0.9 times is 25,000. Give me what is del E. $22,500. Newton meter or 22.5 kilonewton meter. Give me the value of I now, moment of inertia. Del E upon omega square into Ks. Ks is the fluctuation of speed, which is given as 0.01. Satyacharan, you are there? 107?
Yes.
Okay, give me the answers then.
Yes, I'm calculating.
Vinayak, 115. Are you there?
Yes, I'm just doing the sum.
Okay, good. Aditya, no answers from you. 1583. kg meter square. Okay, we still have some time, so let us solve this problem completely. This is equal to Rm square. Now for Rm, we have to get the value of Dm. For Dm, we have to get the value of D naught. For D naught, we'll have to assume what is the surface speed. On 75 kilowatt, what is the surface speed given there? Design data book. What is the surface speed given? Refer the design data book. 1800 meter per minute. Is that the value given? For power less than 75, it is 1600. For power greater than 75, it is 1800. Or the value should be in the range of 1600 to 1800 for power greater than 75 kilowatt. Our value is exactly 75 kilowatt. So which one you think should be better, 1600 meter per minute or 1800 meter per minute? You have to think from the failure perspective. What would happen if the value of peripheral velocity increases? What would happen? From the failure perspective or from the stress perspective? FC increases, right? So if the centrifugal force increases, from the centrifugal force we also get the bending stress. So bending stress would also increase. So you can actually solve it with 1800, and you can see if the resultant stress is still within the limit, then it is safe. But for a lower value, that is 1600 meter per minute, the value will be definitely safe. So there's a chance that you can take. You can try as well with both the values. If 1800 per minute, if this is still safe, then increasing the RM will also increase the value of mass, because mass also has this component of dm. So what do you want to go with? Since we have to limit the centrifugal stress and the value is exactly 75, if the value of power is 80 kilowatt, then it is better to go with a value between 1600 to 1800. But as long as it is less than or equal to 75, let's go with 1600 meter per minute. Is that acceptable? Sania, Harshil? If this logic is acceptable, then let's go with the surface speed as 1600 meter per minute. This is to control the centrifugal stress. Now with 1600 meter per minute, give me what is the outer diameter. .41. So imagine 1.41 meter diameter. This is huge, isn't it? This is big enough. If you go with 1800, the diameter would further increase. So 1.5 meter, 1.5 meter diameter. Can you visualize the size of the wheel, the flywheel? Okay, so if this is DO, the outer diameter, what do we take DM as? We don't know what will be the height of the rim, but what do we take then? Okay, let's go with 1.2 or 1.3. How much? कितना रहेगा height? 60, 70, 80 mm रहेगा, right? Still less than 100 mm, so we can even go with 1.3 meter. We'll check later. Let us assume DM is 1.3 meter, so RM is half of it. And assuming cast iron flywheel, density is 7200 kg per meter square, meter cube. So this is rho into pi dm b h rm square. everything known to you, gave me what is B into H. B into H is 0.4. Zero point 0.5. What is the value of mass that you got for this value of Rm? What is the mass? For 1.5 meter diameter of the rim. Yeah, V by H, B into H should be 0.12. This is correct. So I wanted to check what is the mass you are getting. Who got this 0.4 and 0.5? Arshil, Sania, 0.4. Is that B into H you are getting? Yeah, 0.127 is correct. What is the mass, Sarvesh? $3,749. Imagine this is so heavy. 3,000 kgs. This is the mass of the flywheel. For this much heavy flywheel, your shaft has to be very heavy, large diameter shaft. And so we cannot go on extending the peripheral speed or the diameter to any extent. This is huge, isn't it? 3,000 kg mass. Well, so with B into H 0.127, and what do we assume B by H as? It has to be in the range of 0.65 to 2. You can as well go with B by H as 1. In the last problem, we assume B by H as 0.85. If we assume B by H as 1, this is a square cross-section rim. So what is B and what is H? Point 0.35. So both are 0.35. So what is outer diameter now? Outer diameter is mean diameter plus half of the thickness added on both the sides, so which is equal to H, 0.35. Is that exceeding 1.4? Yes, it is. It is exceeding 1.4. Either you can reduce the value of D mean, or you can have a different ratio here. You can have a different ratio so that this value is not exceeding 1.4. What do you want? You want to try and error with B by H ratio, or you want to reduce D mean from 1.3 to 1.2? Karo? The maximum value of B by H can be 2. You can try with B by H as 1.8, 1.7. Rajwal, what is B by H that you are assuming now? Okay. You should normally avoid taking the extreme values like 0.65 or 2, but okay, it's okay. It's not wrong, but a good practice is try to limit it within 2. Make it 1.8, 1.75. But you can as well go with 2. This we just assume this value has to be little less than the outer diameter. Mean diameter has to be little less. But how much less we don't know, because we don't know what is this height in this flywheel rim. This is the rim of the flywheel. This is your outer diameter, which is giving the peripheral speed. And this is your mean diameter, little less than the outer diameter. And this is H. And here, this is B. So when you are assuming B by H as 1, you are assuming this cross section is square. So if this is 1.4, you can go with 1.1, 1.2, some value little less than this. And then we check whatever we have assumed, is that correct? Because if dm increases, this d naught will increase, which means the surface speed would increase. So we cannot go beyond 1.41. So either you go back to dm, assume 1.2 or 1.1 meter, recalculate this for the same b by h ratio and check whether d naught is still within 1.41. So Prajwal is probably trying with b by h as 2. Sarthak, you try with the value of dm as 1.2. I guess Saurabh suggested we go with 1.2 as dm, right Saurabh? We need to decrease dm, b by h is not working for 2 years. Go with dm as 1.2 or even 1.1. Let's go with dm as 1.1. We'll have to recalculate what is b into h. So after this b by h, you have to again check what is d naught. If that is still in the safe region, then you have to find out what is the sigma c value, which is rho v square. You have to find out what is the bending stress, which is given as sigma 2. And the formula is given in terms of v, rho, d, I and h. You'll also have to assume the number of arms, n, which is given as I over here. And you have to find out what is the resultant stress. If that is safe, then all these assumption of dm, b, h, this ratio of b by h, everything is same. If that is not, then you'll have to again redo with b by h or dm or d naught. In the resultant stress, 75% weightage is given to centrifugal and 25% weightage is given to bending. So this completes only the design of flywheel rim. We should have taken 0.9 times of this I. This is the I of complete flywheel. This is I of complete flywheel. What is the moment of inertia for rim? When we are designing rim, we have to take the moment of inertia of rim, which is 0.9 times the total I. I of the total flywheel. This I forgot today, sorry for that. Is the procedure clear? Next 2 to 4 minutes we can discuss if you have any doubts related to gears, belt drives, chain drives, flywheel, any kind of doubt. So this DM, B and H, this is giving you the design of flywheel rim. For the complete flywheel design, you have to also design the shaft, hub and arms. That completes the flywheel design. Based on the torque, you know how to find the diameter of the shaft. From the shaft diameter, the hub diameter values are directly given. And from the bending moment, you have to find out what is the stresses in the arms. From the bending stress, you have to find out the cross section of the arm. We always assume the arm cross section as elliptical. So that part remains the same as that of the pulley. How less we can take. In this problem, we got the height as 350 mm, right? In the earlier problem, we got it only 37 or 40 mm. So it entirely depends upon what is this B into H that you are getting. So many a times you'll have to go with trial and error. So you solve 2 more problems and you'll get an idea how much this should be reduced. 1.3 se kaam nahi kiya, go for second iteration, go with DM as 1 meter. So Prajwal, there is no thumb rule that this must be reduced by 0.2 meters or 0.1 meter. It's not like that. Okay, good. Any other doubt? Aditya, Utkarsh, yes? Yes, somebody was asking me something.
Here, how did we 0.
How did we?
get B into H as 0.1?
Sorry, you're not audible. How did we get what? Louder, please.
Ma'am, she is asking how did we get B into H as 0.127?
Okay. Value of I is known, density is known, pi, dm, rm, everything is known. So B by H, what is your value?
Ma'am, we got like 0.5. Ma'am, DM was considered 1.3 in this calculation. In that also we are getting 0.5 something.
And how others are getting 0.127? Pi is not written in that formula. Volume is its circumference, it's multiplied by the cross section. ये फॉर्मूला दिया है ना मास के लिए. This is what we are using, isn't it? Pi dm, rho pi dm b into h. Pi is not written where, Harshil?
Yes, ma'am. Maybe we skipped that pi in that calculation.
Okay, so you missed pi.
Yes, ma'am.
Okay. Okay, good. Anything else? Please feel free to ask questions. I am really wondering how come nobody has any doubts. It's good if everything is clear. Should I take the credit if everything is clear to you? Sania? Yes, or should I give you the credit? Okay, so I'll stop the recording here. I'll share this recording in the group. All the best for all your subjects, all your papers in midsem. Thank you.